Dude, Sam Elliott's in this movie?
Hey guys, here are your section 7.1 day 3 notes. So this section of notes, or this day of notes, is going to be all about the inverse tangent that we're going to focus on, okay? We saw the inverse sine, we saw the inverse cosine, now we're going to be doing the inverse tangent. So I've kind of pre-filled stuff in for you to kind of make this go quicker because I know my videos are getting long, but like I said, there's a lot to show you with these. All right, so just remember, what do we know about the inverse sine function? The inverse sine function, right? You plug a ratio in as x and you get an angle out as y. However, when the ratio goes in, the domain, the ratios that can go in are ratios between -1 and 1. Those are the ratios that survived the cut of his graph. All right, and then the angles that can come out are only angles between -π/2 and π/2. Quadrant 1 and quadrant 4 angles are the only angles that can come out of the inverse sine function because those are the only angles that survived the cut of his graph. All right, so just to say it again, because I haven't said it enough, the inverse sine function can only spit out angles between -π/2 and π/2. Quadrant 1 and quadrant 4 angles. Okay, then we saw the inverse cosine. The inverse cosine function works like this. You plug a ratio in as x and you get an angle out as y. However, the domain, the ratios that can go in are ratios between -1 and 1. Those are the ratios that survived the cut of his graph, right? All the ratios survived. But the angles that can come out are only angles between 0 and pi. Those are the only angles that survived the cut of the cosine's graph to make the inverse cosine exist. So only quadrant 1 and quadrant 2 angles can come out of the inverse cosine. All right, so to say it again, the inverse cosine function can only spit out angles between 0 and pi, which are quadrant 1 and quadrant 2 angles, okay? Now I've given you this little sheet chart to go with so far. So depending on whether you're using a negative or positive ratio, those are clues as to which of the two quadrants that angle would have been in. All right, so we saw that if you take the inverse sine of a positive ratio, then that's going to spit out a quadrant 1 angle. But if you take the inverse sine of a negative ratio, that's going to spit out a quadrant 4 angle. Then we saw if you take the inverse cosine of a positive ratio, that's going to spit out an angle in quadrant 1. But if you take the inverse cosine of a negative ratio, then that's going to spit out an angle in quadrant 2. And again, all of these ratios have to be ratios in between -1 and 1, right? Because those are the only ratios that you can plug into the inverse sine and cosine. All right, so then I have these little that kind of I always wind up drawing for myself. The inverse sine, right? Here's your unit circle. He can only spit out angles between π/2 and -π/2. So I always wind up drawing this picture and kind of coloring it. These are the only angles that can come out of the inverse sine, all right? So you better be telling me a quadrant 1 or a quadrant 4 angle. All right, now we have the inverse cosine. The inverse cosine can only spit out angles between 0 and pi. So quadrant 1 and quadrant 2 angles. So when you are using the inverse cosine, you better be telling me the answer is an angle in quadrant 1 or quadrant 2. Nothing else, because those are the only angles that these functions are capable of spitting out. Okay, all right, so just skip this part. Don't worry about that. I was just kind of setting you up for how the tangent function is going to work, but let's go right to the graph of the tangent function, right? The tangent function y equals tan x. You plug an angle in to the tangent function and a ratio comes out. Now, if you remember the tangent function, he was made by the y coordinate over the x coordinate, right? The ratio. So then you ended up getting some undefined angles that you were not allowed to plug in because the ratio was undefined. So if you remember, the tangent function had angles that you could not plug in. You couldn't plug in π/2, 3π/2, 5π/2, -π/2, and so on. X was not allowed to be an angle that was π/2 plus or minus any angle that was pi radians away from him times k rotations or revolutions, right? X was not allowed to be an odd integer multiple of π/2. And then the range, though, the ratios that came out of the tangent function were all real ratios, -∞ to infinity, okay? All right, so here we go. So right now, if you look at the graph of the tangent function, you can see that he does not pass the HLT. This is not a one-to-one function. There are tons and tons and tons of y coordinates that are repeating every so many inputs. All right, so it's not 1-to-1. So technically it should not have an inverse. So what we have to do is just chop a portion of his graph to keep to make his inverse exist. So we always start at 0, and let's go this way. If I just look at this leg of the graph, right? Right now, does it pass the HLT? Yes, 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 right? Okay. Now, if I jump to the other side of this asymptote and I try to include this leg of the graph, it will no longer pass the HLT. So I don't want to do that. So we're going to chop it right at pi/2. Okay, and then if I go back, if I work this way from 0, yes, he's passing. Well, you know what? I better do this. Let me give this another one to kind of go off of. There's going to be another tangent function to the left of him too, okay? So if I work from this leg, does he pass the HLT? Yes, 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 right? But if I jump to the other side of this asymptote, and if I try to see if he passes the HLT now, he won't. So we're gonna have to chop it right there again at -pi/2. So we actually just end up keeping one cycle of the tangent function to make his inverse exist. So we end up keeping his first cycle to make the inverse tangent exist. So this will be the portion of the tangent function that we get to keep. So if you notice the way the tangent function worked, if you plugged an angle between 0 and pi/2 in, a ratio from 0 to infinity came out. So these were your quadrant 1 angles and ratios, right? Then if you plugged an angle between pi/2 and pi in, a ratio from -infinity to 0 came out. So this was your quadrant 2 angles and ratios. Then if you plugged an angle between pi and 3 pi/2 in, a ratio between 0 and infinity came out. So this was your quadrant 3 angles and ratios that lived on this leg of the graph. If you plugged an angle between 3 pi/2 and 2 pi in, then a ratio between -infinity and 0 came out on this leg of the graph. So these were your quadrant 4 angles and ratios. And then even if we went back this way, if you plugged an angle between 0 and -pi/2 in, then a ratio between -infinity and 0 came out. So these were your quadrant 4 angles and ratios that live on his graph. So when you look at the portion of the graph that we keep to make his inverse exist, only quadrant 1 and quadrant 4 angles and ratios survive the cut of his graph. So the inverse tangent function is only going to be able to use these angles and ratios. So he's only going to be capable of spitting out quadrant 1 and quadrant 4 angles. So he's very similar to the inverse sine. He's only able to spit out quadrant 1 and quadrant 4 angles, okay? All right, so that is the portion that we keep for this one. All right, so now let's graph the inverse tangent function. Okay, therefore, the inverse tangent function can only spit out angles between -pi/2 and pi/2. Quadrant 1 and quadrant 4 angles. Okay, so here we go. So let's graph it. So here is y equals the inverse tangent of x, right? A ratio goes in as x and an angle comes out as y. But guys, what ratios are allowed to go in as x? What ratios survived the cut of his graph? Well, guys, look at your ratios. Your ratios from -infinity to infinity survived the cut of his graph. So you're going to be allowed to plug any ratio you want into the inverse tangent function, and it's going to be fine because ratios from -infinity to infinity survived the cut of his graph, right? Your domain are your ratios. All right, but your range, the angles that he's going to be able to spit out are only the angles that survived the cut, and only angles between -pi/2 and pi/2 survived. But the kicker is -pi/2 and pi/2 really can't come out of the inverse because they're not actually allowed to go into the original tangent function. So we don't want to include them as angles that can come out. Angles right up into pi/2 and -pi/2 can come out, but we can't actually include them. So they will never come out of the inverse tangent function. All right, we go right up into them. All right, perfect. So now if we go to graph it, right? Well, we know ratios are going to go in, and we said ratios are going to be able to go from infinity all the way to negative infinity. And then angles are going to come out of the inverse tangent function, but really only angles between pi over 2 and negative pi over 2 are going to be angles that can come out of this inverse tangent function. All right, so let's go back and let's grab some points. So technically, you have a vertical asymptote at the angle pi over 2. So if you have a vertical asymptote on the original, I'm not on the screen, sorry. If you have a vertical asymptote at pi over 2, then that means on the inverse function, you're going to have a HA at pi over 2. All right, again, because that's really not an angle that's physically going to be able to come out of the inverse tangent, all right? All right, now we go back. If you had a vertical asymptote at not negative pi over 2, that one's negative pi over 2. If this was negative pi over 2 and you had a VA, then you should have had an HA at negative pi over 2. And then if you have a VA at pi over 2, then you're going to have an HA at pi over 2, okay? So again, you're going to have an inverse tangent graph that is literally squeezed in between these two horizontal asymptotes, all right? Okay, so now the points that we do have survived, we have the point pi over 4 went in and a ratio of 1 came out. So now when a ratio of 1 goes into the inverse, an angle of pi over 4 will come out. So now when a ratio of 1 goes in, an angle of pi over 4 will come out. Okay? Another point on the graph is the point 0, 0. When an angle of 0 radians went in, a ratio of 0 came out. So now when a ratio of 0 goes in, an angle of 0 will come out. So 0, 0 is on the inverse tangent, all right? And then the other point that we have here, when an angle of negative pi over 4 went in, a ratio of negative 1 came out. So now when a ratio of negative 1 goes into the inverse, the angle negative pi over 4 comes out. So now a ratio of negative 1 goes in, and an angle of negative pi over 4 comes out. So now your inverse tangent function is doing this. He's got to connect these dots, right? So we know he's going to go from this dot to this dot to this dot, and then what's he going to have to do? He's going to be drawn and hug that asymptote, right? He's going to go from this dot to this dot to this dot, and then he's going to be drawn towards that asymptote. So his graph should look something like this. It's so spaced out, it's going to be hard for me to probably get a nice, decent picture of it. But it looks like that, okay? So now, according to my terrible graph, sorry, it's a little bit more straight than that, all right? But what it says is if you plug a ratio between 0 and infinity in, an angle between 0 and pi over 2 will come out. So again, if I plug a ratio greater than 0 in, an angle between 0 and pi over 2 will come out. But remember, not pi over 2. He will not be able to come out because he's an asymptote. All right, and what does that mean? So therefore the angle would be in, if he's an angle between 0 and pi over 2, that would have been a quadrant 1 angle. So if you ever have to draw a picture of this later, put the angle, put the triangle in quadrant 1, because that's where it would have been. All right, now notice, look at the other graph. If I plug a ratio less than 0 in, if I plug a ratio between 0 and negative infinity, something less than 0 in, then according to this graph, an angle between 0 and negative pi over 2 will come out. But not negative pi over 2, because he really can't come out. All right, and where is an angle between 0 and negative pi over 2 going to be found? In quadrant 4. So then therefore, if you ever had to draw a picture, put that angle or put that triangle in quadrant 4. Okay, all right, so that's how the inverse tangent works. So he's basically just like the inverse sine, except the inverse sine can spit out pi over 2 and negative pi over 2, and the inverse tangent can't. All right, but they both are stuck with those quadrant 1 and those quadrant 4 angles. All right, so the inverse tangent function can only spit out angles between negative 90 and 90, or negative pi over 2 and pi over 2 radians, quadrant 1 and quadrant 4 angles. So now, since I keep forgetting to do this, let me just go back and fill in the rest of your cheat chart. So your cheat chart, now we know if you take the inverse tangent of a positive ratio, it's going to spit out an angle in quadrant 1. If you take the inverse tangent of a negative ratio, it's going to spit out an angle in quadrant 4, okay? All right, perfect. So let's give it a whirl. So example 1, it says find the exact value. What is the inverse tangent of 1? Well, remember, how does the inverse tangent function work? You plug a ratio in and an angle comes out. The inverse tangent is only capable of spitting out quadrant 1 or quadrant 4 angles, right? This portion of your unit circle are the only angles and ratios that he's allowed to work with. All right, so the inverse tangent of 1, if you take the inverse tangent of a positive ratio, we know that should equal a quadrant 1 angle. So we know the answer to this is a quadrant 1 angle. So now I'm going to turn the problem around. So basically it's asking you the tangent of what quadrant 1 angle had a ratio of positive 1. So now you have to ask yourself, okay, the tangent of what special angle had a ratio of 1? Is it my 30, 45, 60? Was it a quadrantal? So I gave you this cheat sheet. So go to your tangent. You're looking for the angle that had a tangent ratio of 1. And who was that? Right here, it's the angle pi over 4. So the quadrant 1 angle that makes this true is pi over 4. Okay, and again, if you ask your calculator to do this and you're in radian mode, it's going to give you the decimal version of pi over 4. Watch this. If I'm in radian mode, if I ask it what is the inverse tangent of 1, it's going to say it's 0.7853. And guess what? Pi divided by 4 is 0.7853. It's giving you the decimal version of this angle in radians. Okay, all right, look at the next problem. What is the inverse tangent of negative root 3? Well, remember, the inverse tangent can only spit out angles between the, pi over 2 and negative pi over 2. Quadrant 1 and quadrant 4 angles. We know if you take the inverse tangent of a negative ratio, then it should equal a quadrant 4 angle. So we know the answer to this problem is a quadrant 4 angle. So now turn the problem around. The tangent of what quadrant 4 angle would have equaled a ratio of negative root 3. So now you have to ask yourself, the tangent of what special angle would have had a ratio of root 3? Was it your 30, your 45, your 60? Was it a quadrantal? What's going on here? Well, if you look at my cheat chart, what the tangent of which angle had a ratio of root 3? Now again, the ratio would be negative because it's an angle in quadrant 4, we know. And guess what the tangent of an angle in quadrant 4 is? It's a negative ratio. So that means it's pi over 3. But the answer can't be pi over 3 because that wouldn't be a quadrant 4 angle. So it would have to be negative pi over 3. And you're done. Okay? All right. What is the inverse tangent of root 3 over 3? Well, we know if we take the inverse tangent of a positive ratio, that's going to equal a quadrant 1 angle, okay? So now we know that the inverse tangent can only spit out angles between pi over 2 and negative pi over 2, quadrant 1 or quadrant 4. We already know the answer is a quadrant 1 angle. So now turn the problem around. The tangent of what quadrant 1 angle had a ratio of root 3 over 3. Well, guys, the tangent of what special angle was root 3 over 3? Was it a pi over 6, a pi over 3, a pi over 4? Was it a pi over 2, a pi? What's going on? So if you look at my cheat sheet, the tangent of what angle was root 3 over 3? It's pi over 6. So we need a version or a multiple of pi over 6 that would have landed in quadrant 1 between pi over 2 and negative pi over 2. And guess what? It's pi over 6. So pi over 6 is the answer to that question. Okay? All right, now let's look at these examples. All right, it says find the exact value of. What is the inverse tangent of the tangent of pi over 10? Now remember, what are the inverse tangent and the tangent function? They are inverses. They should cancel each other out. Look how this problem is set up. This one is asking you to take the tangent of an angle. The answer to that is a ratio. When you take the inverse tangent of that ratio, the final answer is an angle. The answer to this question is an angle. So what should the inverse tangent and tangent do? They should cancel each other out, and we should be left with this angle as our answer. As long as this is an angle that the inverse tangent was capable of spitting out, we're done. Well, guys, think about it. The inverse tangent can only spit out angles in quadrant 1 or quadrant 4. Angles between pi over 2 and negative pi over 2. Well, we're working with pi's over 10. So pi's over 10 then, let's see how many pi's over 10 make pi over 2. Well, in order to get 2 to 10, I have to times by 5. So this is 5 pi's over 10. So as long as, if this is where 5 pi's over 10 land, guess what? 1 pi over 10 lands here, and then 2 pi's over 10, 3 pi's over 10, 4 pi's over 10, 5 pi's over 10. So 1 pi over 10 is definitely an angle that landed in quadrant 1, and he would have been capable of the tangent function spinning out. So pi over 10 is definitely your answer. Okay, let's look at this one. This one says, what is the inverse tangent of the tangent of 4 pi over 5? Well, think about how this problem breaks down. If I take the tangent of an angle, the answer is a ratio. When I take the inverse tangent of a ratio, the final answer is an angle. So the inverse tangent and the tangent should cancel out, and I should be left with this angle as my answer. But I'm only allowed to say that's the answer as long as that is an angle that the inverse tangent would have been capable of spitting out. Is 4 pi over 5 a quadrant 1 or quadrant 4 angle? Let's see. All right, well, the inverse tangent can only spit out angles from here to here, right? We know this is pi over 2, and we know this is negative pi over 2, right? Okay, well, if we're working in the world of pi's over 5, right, well, how many pi's over 5 are equivalent to pi over 2? Well, in order to turn 2 into a 5, I have to times it by 2.5. So times the pi by 2.5, and technically this is 2.5 pi's over 5 right here. So if this is 2.5 pi's over 5, and we know this is 5 pi's over 5, guess where 4 pi's over 5 land? 4 pi's over 5 land in quadrant 2. So that can't be the answer to this question because the inverse tangent would never have spit out a quadrant 2 angle. So we're going to have to turn this into an equivalent angle that the inverse tangent would have been able to spit out, or whose ratio would have been equivalent, okay? So look at your inverse tangent, look at your tangent, right? All students take calculus. The tangent is positive in 1 and positive in 3. That means he's negative here and he's negative here. So right now we are working with a quadrant 2 angle that he would be incapable of spitting out. So in what other quadrant would the tangent function also have given us this negative ratio in? For an angle that was in quadrant 4. So that means we can turn him into an equivalent angle in quadrant 4. We can turn him into an angle that would have given us an equivalent ratio, okay? So now, who is your reference angle between 5 pi's over 5 and 4 pi's over 5? 1 pi over 5. So turn that into an angle in quadrant 4 that has the same reference angle. So the same angle in quadrant 4 with the same reference would be pi over 5. But it wouldn't be positive pi over 5 to be in quadrant 4. It would be negative pi over 5. And that's an angle that the inverse tangent is capable of spitting out. So the answer to this question is negative pi over 5. Okay? All right, perfect. Now look at these ones. What is the tangent of the inverse tangent of 4? Well, let's break this down. If you take the inverse tangent, then you're taking it of a ratio, and the answer is an angle. So the inverse tangent of this ratio is an angle. The tangent of that angle, the answer would be a ratio. So these should just cancel out and we should be left with this ratio as our answer. And the beautiful thing about tangent, the ratios that survive are all real numbers. There's no bad ratio as far as the inverse tangent is concerned. So that means this could be any number and we're good. So that ratio is our answer. All right, look here. What is the tangent of the inverse tangent of negative 10? Well, if I take the inverse tangent of a ratio, the answer is an angle. When I take the tangent of that angle, the answer is a ratio. So these functions should cancel each other out, and I should be left with this ratio as my answer, as long as that's an okay ratio for the tangent. But the beautiful thing is, there's no bad ratio for the tangent function. Your ratios go from infinity to negative infinity. So negative 10 is our final answer, and you're done. Okay, so those are all of the inverse trig functions. If you have any questions, please reach out to me. And I would definitely keep this handy All right, this cheat sheet that I gave you, I'm going to send you a picture of it, and then just keep reminding yourself of your cheat chart, and then these pictures help me a ton too. All right, but again, please reach out to me if you have any questions. Good luck.